All right, so today you're going to pick up on slide number 33. So if you remember, we left off talking about what melting, freezing, condensing, and evaporating meant. But there are a couple other special types of phase changes that we're going to talk about before we move on to heating and cooling curves. So I want to backtrack for just a second. If you remember, go back here. Hold on. Gosh, it's not gonna let me go back. That's okay. We'll pick up with this slide. It's all right. Back to 33. Sorry. Freezing and melting, evaporating and condensing. They are all kind of those. You go straight from one phase to another. So from the liquid to the solid, or the solid to the liquid, or the gas to the liquid, or the liquid to the gas, right? Well, the last two types that we're going to look at are sublimation and deposition. And these are our special ones. If you remember from a graph from the other day, there were two that skipped the liquid phase. So they would go straight from that solid to the gas, or straight from the gas down to the solid. So that middle section, that liquid area, never got touched, right? It skipped that phase altogether. And so when we talk about sublimation or something subliming, it goes straight from the solid to the gas. And so the prime example of this is dry ice. At room temperature, carbon dioxide is going to be a solid, right? In room temperature, it goes directly to the gas. It doesn't start to melt, right? It actually skips the melting and goes straight to that gas phase. So it makes it pretty special. Okay, here's our solid carbon dioxide, and it is going to go straight to the gas. Deposition is our second kind of special phase change, and this is kind of the reverse. It's when a gas is going to change to a solid. It's not going to melt first, okay? Or excuse me, it's not going to condense first. Right? So we're going straight from like water vapor in the air to maybe frost that you would see forming on leaves. If you park your vehicle outside and it didn't snow and there's frost all over your windshield, that's deposition, okay? So you have to kind of think about it. If there was no precipitation overnight, how could that have gotten there, right? The only explanation is that there's moisture in the air and the temperature got warm enough got cold enough where you had the warmer vapor in the air touching the colder vehicle, and because it cooled that water vapor in the air, it caused those water molecules to slow down, and it caused this film to kind of form on the windshield or even sometimes on the whole body of the car, right? And so we know that the solid version of ice is the colder version. So the gas version is the warmer, and so the air was a warmer temperature, but the vehicle itself got colder than the air temperature, and so it cooled the air directly around the vehicle, causing it to kind of frost up, all right? So even without any kind of precipitation, a lot of times there will be that frost that forms on our vehicles if they're not parked inside. You see that a lot, like on tall grasses, on leaves. You see that on a lot of different things in the winter, and it's a perfect time of year to experience that because it's January, right? Or almost February, I guess. And so you're dealing with this gas vapor that's in the air that is then able to go directly and settle. If you remember from 8th grade science, we talked about weathering, erosion, and deposition. Deposition was the process of dropping that sediment or those broken smaller pieces. Well, this is basically what's happening. That water vapor is depositing on that colder surface, okay? So just like when you had condensation going from a gas to a liquid, you had the warmer air going around that cold can. The cold can slowed the water molecules in the air that were gas, that vapor, until they slowed enough that they formed clumps and around that can, forming those little sweat drops. So the same process is kind of happening, but you are skipping that liquid phase. So the air gets colder from the car, or maybe the leaf, or the tall piece of grass, or whatever it may be. It's colder than the air around it, and so the cold air, the warmer air, then is around that car, or that piece of grass, or that leaf, and it slows those water vapors in the air, and as they slow, then they eventually start to get deposited or dropped and kind of put that coat or that filming all around the object. And you're going to watch some videos that are going to show this really well. So when you're watching the sublimation of iodine, you'll also see deposition happening in that process as well. And then there's a couple other videos that will show both of these processes really well. Okay, so obviously frost is our main example for the deposition. Okay, so we're going to move into our third and final category for this unit. That's looking at heating and cooling curves. A heating curve is going to be the exact reverse of a cooling curve, and vice versa. If you have a cooling curve, kind of flipping that around, the exact opposite is our heating curve. So once you get one of them down, the opposite is true for the other. So this is going to be a graph that shows the relationship between the molecular kinetic energy and the potential energy within a substance, and we call that thermal energy or heat that's being added to the system. So it's just a relationship between kinetic energy, potential energy, and thermal energy. So thermal energy or heat is being added that causes the temperature to increase. That's a no-brainer. You have a stove, you turn the heat up on high, and it starts to get hotter, right? You increase that temperature of the stove. What's really happening though is the molecules are also speeding up, right? So kinetic energy is motion. And the way to increase kinetic energy is to increase the temperature, and that causes the molecules to start moving and moving and moving and moving even more quickly and more intensely. If the temperature is not changing, but thermal energy is being added, then we get potential energy that is building up. We're going to have a whole unit on kinetic and potential energy. For right now, if you think back to 8th grade science, again, potential energy is the energy of position or the potential to cause change, right? So in this case, it's the potential to cause change. It's like storing up all this potential energy, and then all of a sudden you'll see it do something, or you'll see it kind of reach the next level. And so that's what this is going to be about. We're not talking necessarily about gravitational potential energy or chemical potential energy or elastic potential like we did last year. We're just looking at this kind of in general, very broadly, with the idea that it has the ability to potentially cause some change, right? And this will all make sense as we start looking at some of these examples. So here is a heating curve, very simple. We have temperature along our y-axis here, our dependent variable, and then down here it says heat added for our independent variable on our x-axis. We'll look at a few more that have different labels, but the same general idea. So thermal energy is being added, or the temperature is increasing as we add that thermal energy to the system. So as we add heat, it increases our temperature, which is exactly what you would expect to happen, all right? So don't try to like outthink this or make it more complicated than it is, okay? So if you notice, we have 3 areas where the graph is increasing. Based on our axes, temperature is going up in these 3 locations, okay? Notice the picture for the solid, the picture for the liquid, and the picture for the gas. Those totally match what the characteristics are for those states of matter. We know that, okay? So that is not something new. Okay, so there are also 2 areas where there is a plateau, a flat line. In your vocabulary, you have the 3 P's: plateau, phase change, and potential energies changing. The 3 P's, the plateau means the flat area. Like a plateau, if you're talking like landforms, plateau is like a large flat topped area, right? So these flat line areas are the plateau. These are going to be where the potential energy is changing. and you can see that a phase change is happening. Does anybody know why a phase change is happening, or how we know that one's happening actually? Think about it for a second. How would we know that a phase change is happening? And we talked about this yesterday. Anybody say it's because you see two states of matter? Because if you did, you're correct. Here we see liquid and gas. Here we see solid and liquid. So these two spots, the molecules themselves are showing you that two things are happening or existing at the same time. So let's start at the beginning. Here we are below freezing, right? Here's 0 degrees Celsius, which is the freezing point of water. Below that, obviously everything is going to be frozen. So we have the solid version. Once you reach 0 degrees Celsius, that is when you are going to start to see some melting taking place. Some of the solid is going to go to the liquid, and you can see that. You have both solid and liquid. That's a phase change. I'm increasing heat here, but notice how my temperature is stuck at 0. I am not increasing the temperature. When the temperature is not changing, but you're adding thermal energy, that's an indication of a phase change. So again, the 3 P's, the plateau, phase change, and potential energy changing. So this is where potential energy is changing, our plateau, and we see phase change happening. Once it has all turned to liquid, then instantly my temperature starts to go up again. The kinetic energy starts to go up again, because whatever temperature does, kinetic energy does. And so as the temperature is increasing, right, until we reach 100 degrees Celsius, which match our key temperatures for phase changes, right? 0 degrees Celsius is our freezing melting point, and then 100 degrees is our boiling and evaporation kind of points. So as we reach the 100 degrees Celsius, then that is when some of that liquid has enough energy where it's going to start to turn into the gas form. Once it has both of those, you are putting thermal energy, you're adding heat. But notice, I'm stuck at 100 degrees Celsius. I have plateaued again. I also have a phase change. So this indicates where potential energy is changing, okay? Once the last liquid water molecule has vaporized, evaporated into the gas version, that is when the temperature will start to increase again. At that point, it goes over 100 degrees, and it stays all in just the gas form. It would need to keep that 100 degree temperature or higher in order for it to stay at the gas temperature. If that temperature would drop below 100, that's when you would start kind of the reverse process, and a cooling curve would start. You would start to go backwards into the liquid and starting that condensing, and then that liquid would start to freeze as you would get back to this point, as it would get at 0 degrees Celsius. So we'll talk about that in a minute. But the main things is that I could say, okay, where are the 3 places that the kinetic energy is changing? All you have to do is see where the temperature is changing. Well, I see it go from -40 to 0, I see it go from 0 to 100, and I see it go from 100 to 130. Those 3 places, the temperature is changing, so that instantly lets you know that's where the kinetic energy is changing as well. So whatever temperature does, that's what kinetic energy does. Now, I could also say, okay, where is the kinetic energy staying the same? Well, temperature is staying the same, so that means kinetic energy is staying the same. I'm stuck at 0 here, and I'm stuck at 100 here. So because you can see the temperature clearly on the graph, I always suggest look at what the temperature is doing. You can see that very clearly, then that will be exactly what kinetic is doing. So if I ask you a kinetic question, ask yourself, what's temperature doing? And that's your answer. So it's going up in these 3 locations. It is staying the same in these 2 locations. Now I could also ask you, where is the potential energy changing? Well, that is going to be where the kinetic energy is not changing, because they both can't go up or down at the same time. One's going to go up, oops, there we go. One's going to go up, one's going to go down, right? Or stay the same. You can't have both of them doing the same thing. That doesn't work. That breaks the law of conservation of energy. We'll get into that more in some of our other units. So if I ask you, where is the potential energy increasing? Well, that's going to be here and here, because that's where your kinetic energy is staying the same. So that means because you're adding thermal energy in, or that heat, it has to transfer into something. It has to be doing something. So what it's doing is it's building up all this potential, and it's breaking the bonds of the solid, releasing that, not the bonds, but the attraction, allowing those water molecules to separate from each other. And so it has the potential to change the positioning of the molecules, right? So it's not changing the molecules themselves, it's just changing how tightly attracted they are. Are they packed together like a solid, or are they loose like a liquid? So all of that energy is focused into changing that attraction. It's allowing that to loosen and turn into the liquid form. Same thing happens over here. As soon as you reach that 100 degrees, it's building up and taking in all that heat that keeps pumping into that system. That heat's going in, going in, going in. And what it's doing is it's going into that liquid, and it's allowing those bonds to even loosen more, that attraction between the molecules, and that attraction is able to be lessened even more, allowing those water molecules to now turn into the vapor or the gas form of the water. So these two locations here would be showing you where the potential energy is increasing. I could also ask you, where are phase changes taking place? You could visually see, because remember, the key with phase changes is there's two phases happening at once. So there's two, and there's two. Remember, plateau, phase change, and potential energy all go together. And so those are the two locations that you have the plateau, the two locations that you have a phase change taking place, and the two locations where potential energy is changing. Okay? All right, so let's get the words to this. So one more picture, I guess. Here we see our solids. Here we see our liquids, where they're tightly packed, but not as rigid and stiff and tightly as the solids. And then you see the gas version. So obviously going from the solid to the liquid is melting. From the liquid to the gas is evaporating. And then if we go straight from the gas to the solid, right, we get that, that deposition process. And if we go from the solid straight to the gas, that is our sublimation process. Okay? If we go from the gas and things are getting colder, we go to the liquid. If we go from the liquid and get even colder, we get freezing. Okay, here's the word part. So this is slide 37. So kinetic energy is the energy of motion. Specifically of particles with like atoms and molecules, it's related to temperature. So as kinetic goes up, the temperature goes up. There is that direct correlation or relationship. Potential energy, like I had mentioned earlier, is the energy or the arrangement of particles. So the spacing between the molecules in this case. So it's that arrangement, energy of position. And so the temperature does not change during a phase change. The energy is actually transferred into the potential, which is why the plateau, the phase change, and the potential energy are all kind of linked, and that's why I came up with that kind of weird vocab term of the 3 Ps. Phase change, plateau, potential energy. Okay, so again, this is what it might look like. Now down here, it shows time. Obviously, we know that this time is really talking about as time goes on, as heat is being added or thermal energy is being added into the system. I like the other graph better because it shows that you're putting thermal energy in down here, right? And that's what's actually happening. So even though they say time, we know as time goes by in minutes, you have temperature or thermal energy is more accurate. Thermal energy or heat is being added in, and that has a direct effect on the temperature, which we know because this is our dependent variable, our axis, and this is our independent. So as time goes by, it will affect our temperature here. So here I see 3 areas where my temperature is going up. I see 2 areas where my temperature is staying the same. Remember the connection. Whatever temperature does, that's what kinetic does. So any question I ask you with temperature, just look to see what the temperature is doing, okay? So if I say, give me the 3 locations where kinetic energy is changing. What's changing where the temperature is increasing here, it's changing where the temperature is increasing here, and it's changing where the temperature is increasing there. If I say, tell me the 3 locations where potential is changing. Well, has to be here and here because potential energy, plateau, and phase changes all go together. So again, if I say, where would a phase change be taking place? Hopefully you're picking out the 2 plateau areas. Okay, so let's look at the little details. This is where you're going to have a solid. There's no cute little diagrams up here to show the molecules this time. So we have the solid where we have kinetic energy going up because temperature is going up. Now we have a phase change. It is a plateau. This is where potential is increasing. So it's taking all that heat that's being pumped into that liquid, or excuse me, into that solid ice at this point. It's taking all of that and it's able to cause the arrangement, the attraction between those water molecules to weaken, and it allows that solid to start to change into the liquid, where the liquid molecules are able to have a little bit more freedom, they have more space between them, and following all those characteristics of a liquid. 2 phases are taking place, it's a plateau, and potential energy is increasing. Now we have another kinetic energy increase, and I know that because my temperature is going up. I know that this is water again because I'm at 0 degrees Celsius and 100 degrees Celsius is where I see those phase changes starting. Remember, we use water for almost all of our examples, but not all materials are going to have a freezing and melting and boiling point like water does. So even though we know water has those special 0 and 100 degrees Celsius freezing and melting points and boiling points, we know that other substances have their own unique substance, or excuse me, temperature. Okay, so here we have boiling, okay? And again, this is a plateau. This is an increase of potential energy. So again, you have the liquid. All that thermal energy is pumping into that system, but it's not increasing the temperature, right? Because I'm stuck at 100 degrees, 100 degrees, 100 degrees. And when that happens, all that energy is going into releasing the attraction even more between the water molecules. Now they have the opportunity to move even more, and you're getting some of that transferring into spacing even farther apart, causing them to turn into the gas. When all of the water molecules, the liquid water molecules, have changed into gas, now we have an increase in kinetic energy again because we see that change in temperature, that increase in temperature going on. Okay, so the heating curve below is going to show the constant rate of heating over time. This is called an endothermic process, and we've talked about this a little bit before in one of our other units. Endothermic means it is taking it in. Heat is being absorbed. So as time goes by, thermal energy is being pulled into that system. Think about it logically. If you have a solid ice cube, to get it to melt, it needs to get hotter, right? It needs to increase the temperature. The way to do that is for it to be able to absorb, take in heat from its surroundings. Okay, so if you look here, from A to B you have a solid. From B to C, you have both a solid and a liquid. C to D, liquid. D to E, you have that plateau area, phase change, and potential energy changing. You have both liquid and gas. And then here, E to F is just gas. So again, I could say, where do you have an increase in potential energy? A to B, C to D, E to F. Those match the rises in temperature that you see here. Okay, so again, whenever you're trying to answer kinetic energy, look at what the temperature is doing. They go together. Whatever temperature does, kinetic does. Temperature goes down, kinetic goes down. Okay, as you look, I could also say, hey, where's the temperature going up? Well, A to B, C to D, E to F. Okay, I could also ask you, where's a phase change happening? B to C and D to E. How do you know? It's a plateau. And if you had pictures, you would see both solid and liquid molecules here. You would see both liquid and gas molecules here. 2 phases present indicates a phase change. Endothermic, taking in. This is the process that is taking thermal energy in from the surroundings. So the hands taking in the heat from the hot chocolate, okay? That would be the description of the endothermic. It's associated with heating curves because you have to take heat in to heat the solid ice or the solid material, whatever it is. So you're in endothermic. They kind of sound alike. So focus on the hands absorbing the thermal energy. So the hands are getting warm just like the solid ice cube was getting warm. Okay, another way to look at this, here we have our special temperatures, right? 0 and 100, we see that start our phase changes. So phase change here, phase change here. Okay, we have water and ice, water and steam, which is our gas version. 2 phases, plateau, that means a phase change is happening. That also means that's where our potential energy is changing. Our 3 kinetic energy changes are here, here, and here. We have 1 single phase at each location. I also know that the kinetic is changing because I can visually see the temperature changing. It's going up here, it's gone up here, and it's gone up here, right? I go from 100 to 140, I go from 0 to 100, and I go from -20 to 0. Watch the temperature. If you see it increase, that means kinetic is increasing. If the temperature is not increasing, that means kinetic is not increasing. All right, and if kinetic is not increasing by default, then that means the potential is, okay? Because you're putting thermal energy into the system, it has to be going somewhere. It can't just disappear, right? It's the law of conservation of energy says you can't just, create it and you can't just destroy it. So it has to be changing into something. And again, I like this one again better than time. It shows thermal energy being added, not just time going by. Even though we know as time goes by, we're actually adding thermal energy. I just like it to be very clear so that there's no confusion. Okay, so the temperature remains the same during a phase change, so it remains constant. So I think you just have that to fill in. Okay, and then looking at what's happening. When we're talking melting, a solid to a liquid, right? We need the attractive forces to get broken. We need those rigid attraction, not a bond, and I've said that and caught myself a few times. It's not a bond that's keeping water to water molecule. It's just an attraction. And so if you weaken that attraction, you allow them to separate a little bit, all right? So by adding thermal energy or heat, that's what can help weaken or break the attractive force. And so evaporating is continuing this idea. It's putting energy into the system, an endothermic process, putting that energy in so that it is able to go from the liquid to that final stage of going to a gas. This is where all attractive forces get broken. That's when you get the gas that's just wild child, right? Those molecules are able to move all around, right? Solids are tightly packed, the attraction gets weakened, and you get the liquid. They can move around, they have some space, and then you add even more thermal energy and you get the gas version where they're able to go all over the place, they're able to move wild, they have lots of space, and all that thermal energy is transferring into that kinetic energy. Because that's what's actually happening, right? You're just transferring that type of energy, thermal energy into kinetic or thermal energy into potential, depending on if you're at a phase change or if it's already changed into all the new form and you are in that heating curve back on the rise with the temperature. Okay, so steam, sweating, all of those are examples of that evaporating taking place. Okay, so, oh my gosh, we can learn so much from a heating curve. I can probably ask you like 20 or 30 different types of questions on just one graph alone. There's so much information packed in there. So, you have this graph, I believe it's in the bottom right-hand corner of your notes. And so it is going to match, the segment AB is going to match that. So I couldn't have the graph and the descriptions all on the same slide. So you have the graph this goes with on the bottom corner of your notes, okay? So you're looking at the heating curve, section A to B. This is the heating of a solid. There's one phase. Kinetic energy is increasing because temperature is increasing. Then as you go from B to C, it's one of those plateau areas. It's flat line. This is where you start the melting of a solid. There's 2 phases present. You have potential energy increasing because kinetic energy is constant because the temperature is constant. Again, use the temperature on the graph to kind of key in that the kinetic is not changing because the temperature is not changing. In this case, it's probably, if it's water, it's stuck at 0 degrees Celsius. Then as you go from C to D, this is where it starts to rise again. You get that angling up on the graph. It's the heating of a liquid. You only have liquid, so there's one phase present. Kinetic energy is matching what temperature is doing, which is increasing. And then finally, D to E. This is another plateau area. This is when you have reached probably that 100 degrees Celsius. The temperature is constant, 100, 100, 100, 100. And because the temperature is constant, the kinetic is constant, okay? 2 phases, it's a plateau, potential is changing, the 3 P's. And so finally we get E to F. Once all of the attractive forces have been broken, so not the bonds, but those attractive forces, once they have all released from the liquid, you get the gas version, sorry, I keep hitting my mic, and those molecules get to bounce and fly all over the place, lots of motion, lots of space between them, and they are steam or that vapor version of the water. 1 phase, kinetic is on the rise again. We see that because the temperature is on the rise again. And so when the kinetic is constant, it's because the temperature is constant and not increasing. That is extremely important. And then remember the 3 P's, the plateau, the phase changes, and potential energy. Okay? You're gonna watch this video, it's in Google Classroom. Notice it's gonna show a block of ice with a thermometer probe in it. And so it's gonna be taking the temperature and it's gonna translate that and actually create a heating curve, kind of sped up so it's not real time. But they're gonna create a heating curve based on that solid chunk of ice having thermal heat added to it and watching it melt into the liquid and then watching it vaporize and boil and turn into all the gas version. So you might want to watch this one a couple times in Google Classroom just because it is a little bit quick, and once you kind of realize what you're looking at, sometimes it's over at that point. So you will be watching this graph in the background, but then also watch the chunk of ice as it actually melts and then it actually starts to boil, and then as it actually starts to vaporize and evaporate into that gas version. So we will go ahead and stop there. Make sure you watch all the videos in the notes that are posted in Google Classroom.